you get one more week.
Yeah. Thank you.
I had the grade column created already.
Yeah, there is grade column,
Yeah,
but in
but
the assignment there is
okay.
no attachment. No PDF like that. Yeah.
Okay, then finish this one then. We will continue the semiconductors next week. So last time we talked about the effective mass, right? So you might remember. So basically, effective mass is given as the second derivative of your, or the curvature of your the dispersion curve, right? Yeah. So then if you look at different, so then also here we know your effect, the curvature is much higher. That means the band mass is lower, right? Because the curvature is in the denominator. So here curvature is small, that means you have larger. So if you look at some band structures, valence band and conduction band, sometimes you feel something like this, and then you will feel sometimes these two peaks coming, one from the whole band, one from the heavy hole and the light hole, right? So these are things sometimes you need to. Okay, today I want to quickly talk about something called a new concept for holes. So why is this holes important actually? That's a pretty clever idea. So if you say semiconductor, right? You have some band gap here. If I promote some electron from here to here, now electron is here, right? What happens is electrons from the valence band, it goes to the conduction band to participate in the conduction process. So here now we have kind of empty state, right? Because that electron is already given. So if you want to theoretically address this one, suppose this has a n number of electrons in the valence band. So now if you do this one, you have n minus one number of electrons, right? So that means you need to consider all these n minus one electrons in the valence band. That is not easy. So for that, what they try to do is represent just by one quantity that will represent all the n minus one states. So then it makes much easier. Here it's easy, right? You have one conduction electron comes here, so we know the k vector and everything. We can study the conduction mechanism of that conduction electron. How about here? You have n minus one electrons here, right? So that's a many-body system. So that's very difficult to handle. That's why they came up with this whole concept. Instead of considering this n minus one, they say it is exactly same as considering one empty state here. So that means this n minus one I can remain in electrons, right? Remaining electrons are equivalent to just one empty state. Empty state. That's all it says. Now we can actually, if you look at this one, for any, so if you have a symmetric band, so typically we say J's, numbers, negative J numbers here, positive J numbers here. If I write, say, K J, that is, this is K, right? So that means Kj means this value here. If K minus J means this value, that is negative, right? That means Kj is always negative of K minus J, right? So, because, Kj. So here, if I take Kj, the J1, same as if we have, because Kj, both sides same, right? If we have plus 5 here, you have minus 5 here. If I put minus sign in front, you get the same number. So now just think about filled band. Filled band means what? You have all the electrons filled in the valence band. So all the states are filled up to here. So then how many states you can have? Because each state can have 2 electrons, right? That means you can have n over 2 states, right? So n over 2 will give you n number of electrons. So that means I can write this Kj, all the j vectors going from positive or negative 1 to positive or negative, whatever your n minus 2 value. What is this sum of this one? For any electron here for positive j, you have equivalent negative j here, right? So that means if I say, suppose this is k1, this is k minus 1, right? k1 plus k minus 1 and you can say k minus k1, right? And k2, then minus k2, because for every one you have another minus 1 here, right? When you add this one, what do you get? Basically 0, right? So now I can write this expression exactly same way, except I don't consider this. Suppose this is my missing electron. Suppose this is jth one. I can write this one as j goes from so j entire range except the whatever. Suppose what is that jth one? Or, yeah. So if I consider I here, I is not equal to that jth one. So that means I can write kj. So here, exactly same thing except the k corresponding to that jth state, then I have to add that one here, right? So that means I have to add k, this these are I values, so k, j value. This should be 0, exactly same thing, right? So here I just, it's more like this one, like 1 plus 2 plus 3 plus 4 plus all these, then I can write as 1 plus 2 plus 3 without say 4, like 5, 6, then plus 4. Same thing, right? So that's what we write here. Is that clear? Here I have I not equal to j. That is the electron we are talking about, promoted to this, say this is jth one, promoted to this one. Is that clear, everybody? So it's a different way of writing that one, right? So that means I can write this everything equals minus kj. If you take this one out, that is minus kj. Also we know minus kj is k minus j, right? Because these are plus 1 plus 2 plus here minus 1 minus 2 minus 3 and so on, right? So that means I can write what is this? This is the sum of all the n minus 1 states, right? That is equal to just one wave vector that has k minus j. So that means rather than considering all the n minus 1 states here, you consider only one state that has wave vector of k minus j. So that's what we say whole. So otherwise you have to consider, if I promote one here, you have n minus 1 state, right? That's very difficult, anybody problem. Now instead of doing that, we consider only the k minus j state. Is that clear? This little you have to understand. So same way we can write, if you write your total current for a field band, what is the total current? 0, right? Because if you consider E and V, right? If you consider K going from, I 1 plus or minus 1 to plus or minus n by 2 from both sides, right? Just like before. If you add here, just put sign of this one, this should be 0, right? Again, I write this one as all the state except for that jth one. Then I add that term, just like this one. So that means I can write, this is just the current coming from all the n minus 1 state, that is equal to exactly E, that missing state velocity. So that is the, basically you can show that incomplete band with state plus j empty, right? That's what we are talking about. Behaves just like a positive charge, because this is now positive, right? Because here we considered everything negative. When you move to this side, that becomes positive. Now that behaves as a positive charge. What about the wave vector? That is more like k minus j, right? So that's what we call the whole. So that means if you take the whole, these are the, then also we can show, just imagine these three conditions for a whole. What is the first one? K vector, k j, k minus j, right? So because all these have k j, so if you look at actually something like, ideally it is something like this. If you suppose make your electron goes to here, now this is electron, then this is empty state, right? Ideally, if you consider this as kj vector, right? So really whole has what? K minus j. It corresponds to something here, k minus j state. So what we don't see that one, we just assume if you move to here, you have a hole here. So that's basically what is the charge of this hole? It's positive, we showed that one, right? This has current coming from plus E, so these are all electrons negative. Then also is velocity. If you consider, how do you calculate the velocity? Velocity is basically the E over dk, right? If you do that one, you can see from the negative side your slope is different, right? This one and this one. That means velocity actually doesn't change. So they both have the same velocity. Electrons and holes velocities are same. But the charges, this one has negative charge, this one has positive charge. This one has wave vector kj, then this one has k vector k minus j, something like that. That's basically the charge is, also we talk about the charge, right? Yeah. So charge is, we can just talk about that. This is basically the definition of now you can see how easy it is, right? Rather than considering all these n minus 1 state, you consider only one state that has opposite charge and opposite k value, right? So then how about the effective mass of holes? So if you write Newton's second law for the holes, how do you write the Newton's second law? mass times acceleration equals plus E, right? So for the electron, me times this one equals, we want to find what is the sign of this one. So that is minus E, right? So electron. So now we showed the velocities are equal. The velocities are both the electron and V hole velocities are equal. So that means velocity means using this one, velocity means dE over dk, right? So we know for this side your slope is negative, this side your slope was positive. If you do that one, so just take in the derivative, you can show that it has negative. So if you plug in your mass from here, dE over dV over dH, so you get mH equals minus m. So that's another important difference is your holes have now mass mH that is opposite of your electronic mass. So holes have, if you have positive, it depends on, right? So even electrons in the conduction band, right? So here we have your curvature, certain value. If you get this one, curvature is opposite, right? So that's why your mass electron effective mass will be opposite. Is this clear? Because dV over dt is basically your the slope, right? That's why you get negative. So then if you write your equation in electric and magnetic field, how do you write for electrons and hole? For electrons we write total force as minus E plus V cross P, right? For the hole, this will be basically plus, if your charge is now plus. So that is the equation of motion for the hole. So you can see this is how we started doing the hole effect, right? When you did that one, we have negative sign here. Now if you have a hole, then the sign will be opposite. So that means if you, for the holes, if you have material, your conduction is dominated by holes, your hole effect can be positive. So metals always, your hole effect is, or hole coefficient or hole voltage, they are all negative for metals, right? Because conduction is controlled by the electrons. But there are certain, especially in the semiconductors, or even some metals like bismuth, zinc, so they have your hole coefficient positive. That means it's mostly governed by these holes. This whole concept is little bit tricky. Only thing you need to understand is, rather than considering n minus states in the valence band, you just consider only one missing electron, right? So that they have the properties of this k is minus k, this minus k, but velocities are equal. So hole velocity and electron velocities are same. The mass also, they are opposite, right? That's only, or charges also different. This has positive charge or negative charge and positive charge. That would feel good. Let me continue for another 50 minutes. So now I want to talk about just two different band structure calculations. One is called the empty lattice bands, and one is the tight bundle model. So I think everybody should know these two. The empty lattice band is very simple. So basically, everybody is familiar with this relationship, right? Ek is same as Ek plus or minus G. So that energy same mass, right, within the first Brillouin zone. but we know Ek is given as, what is this value? That is basically K plus or minus G squared, right? E squared K squared over 2m. E squared, the H squared, 2m times, is that clear? So now what we are going to do is, we are going to assume maybe some simple, maybe BCC structure. So then we can write our G and K. So how do you write G? G vector is basically HKL in terms of its the reciprocal space unit vectors, right? So you can write your G as, everybody agree with this one? ABC means reciprocal space unit vectors. Remember how you get ABC from simple ABC, that triple product and all. So this is HKL, right? Is this fine? So now if I write my A for a simple cubic structure, it can be even any cubic structure, you can write as 2 pi over A times, this is unit vector, please remember. Remember this one, 2 pi over A, because if that is constant is A in the real space, the reciprocal space is coming as 2 pi over A, right? So that means I can write my GKL as H times 2 pi over H. Is this clear? Okay, now let's write K vector, because this is what we are going to do, right? So E is given by H plus squared over 2m G plus or minus K squared, right? That's what we are going to do. So this one we wrote now as this one. How do you write K? K is basically Kx, Ky, Kc. Then that one also I can write as, but this is something you should not get confused. So I just write it like this. K as 2 pi over A times, this is actually Kx value. So I just write as XYC because these are the parameters we are going to use. Really this XYC means these are Kx, Ky, Kc, because these are the reciprocal space vector, right? So that means K I can write as 2 pi over A times, this is Kx in the unit vector direction. Is this clear for everybody? So now what we have to do is, for this only thing we have to do is just calculate E for this different Kx, Ky, Kc. Kx, Ky, Kc. Please remember this XYC means, what are those? They cannot be real space, right? They have to be, this XYC means really Kx, Ky, Kc. So now also if you look at, just simply, if you look at this band structure, remember our 1, 0, 0 direction like this, 1, 1 direction like this, right? So this is, we call the, even this one, endpoint. So in the 1, 0, 0 direction is go from 0 to 1. In the 1, 1, 1 direction it goes from 0 to only half, right? So it doesn't go all the way. So that means your X, that this is Kx actually. This, remember, these are Kx values. These are going from 0 and 1. These are going from only 0 and half. So that's it. So now if you calculate your the band structure, so you can see from this gamma point to H point, this is 1, right? 2 pi over A. This is half point. This is also 1. So X, Y, C, they H point in the both direction that can go up to 1. But in the diagonal direction, it only goes to end point. This is the reciprocal space. I think that whole thing is now, since you know these two equations, that calculate your energies for different, this XYC, for different HKL values. That's very simple. So that means this is the equation, right? So this one I can write as, if you take everything out, this is X minus A. This is Kx actually, right? So some parameters. So in terms of, because it's not really Kx, this K x becomes this x times your that unit vector in that direction, right? That's what it is. These are some parameters. Ideally, I like to write it like kx value, but these are just simply so this is the final equation, right? So now you can draw the band structure at any direction. So if I look at G is 0, 0, 0, that means what? Your H, K and L are all zeros. So then if you plug in here, so if you look at this one, so here this example is for BCC structure. That means your H plus K plus L is always even, right? That's the condition. So now if you do this one, just put it, yeah, so in the, if you look at the x and y equals 0 plane, so that means your x is 0, sorry, y is 0, c is 0, then only you get h squared. So sorry, h also 1, right? So you get x squared. That means e 0 times x squared. So you know how to draw that one, right? This is simply parabola, so that means your this one becomes more like a parabola. This is this in the 0, 0, 0 direction, going through origin, right? Y equals x squared. So that is G0, 0. How about G1, 1, 0? 1, 1, this is 0, right? So if you do that one, but 1, 1, 0, you can have many combinations, right? So basically then you get, so if you look at this plane, y see both 0, y see both 0, but here then you have x minus 1, then you have y 0, but k also 0. The next one is L, sorry, k is 1, right? L is 0. If you plug in that one, you get this equation. So you know how to draw this one, right? This is a parabola, but it doesn't go through 0, right? So you have, still it's a parabolic function. If you want to go through 2, 0, 0, this is 2, 0, 0, then you can calculate all this here. So that's how you do this empty lattice approximation. If you draw all these, you can see this is that 0, 0, 0, 1. So others, they have some offset, right? You can see how all the band structures coming from different HKL direction. I think I don't feel good, so I will stop here. Yeah. So it will be, I don't know. So I will continue Thursday. So, once again, we have to do something for the lab. So let's go.